Thank you, Francis, for the introduction. So they asked me to keep the timing very sharp. I will skip some slides in order to keep the total timing. So, good afternoon, ladies and gentlemen. So the theme I have today is the subject related towards high efficiency HVAC system in the Mediterranean region. And the content says first some basic considerations. Sorry, I have to take my paper because the screen is too far for me. Some basic considerations, then the Dieryckx experience, and then the indoor air environment quality. And what can we do in short term, and what are the challenges? So basic considerations. So in the international agreements related to energy efficiencies, we have several basics. So first of all, we have the Global Paris Climate Agreement. We have on the EU the Low Carbon Roadmap, the Eco-Design Requirements, EPB, renewable energy sources. Every 3 years we need a national energy plan. And we also have, from 2016 onwards, the EU strategy on heating and cooling, and the winter package, which is combining several directives and in order to come to a coordinated action. Energy efficiency is already a center today on the regulations, on product developments, and on all global agreements. You can see that there is a clear impact of using the energy label for houses, but also for products. This is well known by you. The next item is related to the Energy Performance of Buildings Directive, and I will not go deeper in that. There were already too many presentations on what is the mechanism, so I will skip that one because it doesn't bring any news for you. But I like to repeat the hurdles that are there in the race towards NZEP rating. So the first hurdle is the building needs, that's the shell. The second is the technical installation. That's what they call the building use. The third hurdle is the non-renewable primary energy. And finally, the last hurdle is how to compensate this non-renewable energy by renewable energies to come to an energy balance. These hurdles are very important. They have been already explained, but we have to remember them very well. And why is this so important, this performance of buildings? Actually, if you look deeply, the buildings have for 41% responsible of the energy use in Europe. And from that 41%, 80% is going to HVAC. So that means that the impact we have on the total targets to reach the reductions and to have the renewable energy is very important. One of the items that is coming always back and is the Eco-Design Directive. And this is in order to reduce the energy consumption. We had already requirements on air conditioners up to 12 kilowatt from 2013. And by that one, for example, non-inverter systems disappeared practically from the market. Air-to-water heat pumps and gas combustion boilers are regulated from 2015, and this year also chillers and VRF systems came into the picture. We had 3 climate zones in heating, 1 in cooling. It's very clear the test method is considering part load conditions. 4 part load conditions are required to declare by the manufacturer. And very important is that up to now it was required to have a public website for the manufacturers, but very soon there is coming a European database where the manufacturers have to put all the data into the database. What is the impact now of this eco-design? This gives just an example. It was recently reported by the Commission for units up to 12 kilowatt. The red ones are the efficiencies before the requirement. The blue one are the efficiencies after the requirements came into force. But there is more than that. If we look to the real roadmap for our products in the future and our business, if we look 2010, 2020, we are looking mainly to theoretical performance. You all know if we do energy performance of building calculations and we need to certify them by authorities, that's paperwork. We calculate the shell, we calculate the technical performance, the performance of the technical installation, and we submit the document and we get an agreement. That's what it is today. So important is this calculation, the climate bin, the temperatures are most important. But from now on, we are coming more and more in situations where they ask real performance. Certifications for buildings, and they go to measured energy consumption of these buildings. So we are coming into an action where first you have the manufacturer and constructors of the buildings, manufacturers of equipment. We come to the status where you are monitoring the systems and where you have experts in order to improve the performance of the buildings. But there is coming a new stage also. From 2020 to 2030, we are going to a smart community. And in the smart community, we are also going with measured performance, but we are going with demand response. And in the demand response, we will have the situation where you have dynamic pricing of the electricity, for example, or the gas, or even the water. And this will ask another action for the equipment and the communication. And there we will start speaking about the reaction times of minutes and seconds, where in the previous one we speak about days and months in order to improve the performance. Here we speak about minutes and seconds to improve the performance related to energy consumption. Also, where we had in the first stage just the manufacturers of the building and the products, the second stage the building experts, there are coming much more parties in the future. We have to be prepared for it. What are now the directions and opportunities in the Mediterranean region? It was already brought before. Life cycle cost optimization is a general guidance. We should not forget that. But describing the limits for the different hurdles that I mentioned for the Mediterranean region is most important. And the unification of the approach in the climate zone of the Mediterranean region to optimize the product development and to accelerate innovation. If you don't unify your requirements in the whole region, you are not accelerating innovation. Improvement of the building shell, yes, but to a life cycle optimum. Don't do too much. In the northern part of Europe, they have learned that too much is not working. More attention to higher indoor air quality and indoor environment quality requirements, combined with better performance for these systems. Of course, NZ buildings are huge opportunities for this region. You are very lucky. In the northern part, if they need heating, they don't have the PV panels at the same time. But in the southern part, cooling and PV panels is matching rather well. So it's very clear that cooling is more sustainable than heating. Let's use that sustainability. Cooling loads and PV energy are very well matching. And the actions you cannot do all together. You have to look on midterm and you have to look on long term. What is now our experience as Dieryckx up to now? We made some research on NZ buildings already in 2010 to 2012. In Germany, we had the office, there was an office built, and these people wanted to make it an NZ building. So the architect, we let them free about the shell, according to the German rules. And then we had to introduce the the technical installations in order to come to an NZEP building, including PV panels. Everybody was wondering about how many surface. We only need 27% of the surface of the roof to achieve an NZEP building. And how did we do that? First of all, we introduced heat pumps in the whole system, inverter technology, and also energy recovery and the ventilation. And together with this, the total steering. So on the paper, we had a very nice result about the energy performance of the building to come to an NZEP. But of course, it is most important to realize that. And as you see in the right top corner, you could see that we actually came to a result where we had delivered more energy from the building to the net than what we used after 1 year. So we had a concept in this building, and what we did, what actually we reached in the first stage, but this is not enough. We went with the 7-step approach, because just having it on paper, it's not enough. Also the commissioning, we did a nice commissioning, but this is not sufficient. You need to do more if you like to read an NZEP. So you have to monitor the things, and you have to look actually to what is not so perfect in the actual use of the system. And yes, in the beginning, we thought we will never reach this NZEP. But at the end, it was very easy to reach it. So by monitoring and optimization, we could come to an excellent result. And we are still monitoring these systems because NZEP is not something on paper. It's not something in commissioning. It's something you have to do continuously. But there are some advantages on NZEP. I will tell you later about that one. Another aspect that we did in our research in southern part of Europe, specifically, was on a renovation. Renovation is very important. New building, fine, but this is not the big part, 3 to 5% of all the buildings. But the renovation is a huge part. So at the moment of renovation, you need to decide some measures, but also some new equipment. So what we did, we monitored the equipment the year before the replacement in order to see very well the pattern of use, the consumption, what is happening. And there we could monitor and see what was the difference between the calculation and the reality. So in most of the installations, we could see that actually the maximum load of the system was far below what was ever calculated. And we measured the performance, and we came that the performance of inverter technology was better than non-inverter technology, but only 2%. Because the unit was working at extremely low loads. So then we monitored and we replaced them with a unit that's only half capacity of the previous one. And we could immediately achieve 20% saving. Of course, the unit was not as expensive as the previous one, which was an additional advantage. So proper sizing of the equipment is most important. And therefore, we have to be very careful in the calculations. We also have to take care with safety margins that are sometimes far too high. We have to consider that there is new lighting coming at the renovation like LED instead of, let's say, the warm lighting. And we have to look very carefully to the ventilation and the ventilation rates and whether you use energy recovery or heat recovery ventilation. We did a similar exercise with chillers in a building where because the load was the same there, we replaced them from non-inverter to inverter. 20% saving on energy. So we can do something. And then we also investigated, we did some projects because they told us we have to look to other solutions like absorption cooling, absorption chillers, etc. So we did an exercise and we looked in Italy in an office of 1,000 square meters and a small office room of 50 square meters, and we compared a direct expansion system, VRV, and a SkyAir unit. We combined with PV panels, and we compared this with an absorption chiller with solar thermal. And both are working, but we looked also to the payback period and the economical aspect. Because making an NZEP on itself, that's not the art. It's not an art at all to make an NZEP, it's very easy. But to make an economical feasible NZEP, that's the art. So that one we have to take into account. So we checked with these two technologies. And the first one, we came with the absorption, we came with a payback period of 213 years, which is not realistic, of course, to invest for. And the Dieryckx systems with the PV panels, we came around 4 years payback. Of course, there were some incentives for the PV panels at that time. We did the same with the bigger installation, sorry, the smaller installation there, the payback from the absorption was even much more. I will not tell the figure here, but the other one was 5 years. And then you say, yes, but you have the incentives for the PV panels. But we checked, and in the past, yes, the investment was quite high for PV panels, and the incentives were high, and the payback was something like 4 to 5 years. But if you see today where the incentive disappeared, the price of the PV panels drastically dropped, and the payback remains 4 to 5 years. So our conclusion was made related to the required technology. And maybe the absorption technology will evaluate, but they have to do a very big effort to drastically reduce the investment cost. Another project which is very important for this region is a project that we started in Portugal, and that was related to cooling demand response. You have seen in my picture for the future what is coming. So we are preparing ourselves, and we have set up a project, 4 office buildings, and the target is very severe. It's a fast demand response, 5 minutes. Normally, they take 15, 20 minutes. This is a 5-minute demand response system. Most important. And it is important in Portugal, and not only in Portugal, I think for the whole Mediterranean region, you have a similar issue if you go to more renewable energy. So Portugal has a lot of wind, but also hydro, but they also come up with a lot of photovoltaic. And they have, of course, electric power demand that is increasing in generally. So how to manage these and how to come with these peaks and these dips, how to manage this? And can we do something? So yes, for the air conditioning, we can do something. So when we are demonstrating 2 projects, one project is with the conventional power company, where the power company is supplying the electricity to the equipment, and where they ask to Dieryckx to control the equipment depending on the availability of renewable energy or peaks in the power supply demand. So these things are going from the power supply company to the Dieryckx monitoring system, going to all our systems, let's say, in Portugal. I can tell you that's a huge power plant as a virtual power plant, this air conditioning. Next to that, we have new power companies. They call them the virtual power supply companies. Actually, they have equipment already in place to do demand management and to react on systems. They have communication. So also there, we are communicating with our equipment directly, but we are monitoring that all the comfort is done and that actually, if we need to change and optimize the software and the equipment, that we can do that. And here you see again how it looks more systematic. On the left side is the new company. So that's a local connection. And you see that the signal is going directly from the power company to the equipment and return. On the right side, this is the traditional power company. The signal is going via the Dieryckx server up to our equipment. You can ask here, what's the big difference? Well, the big difference is the liability on this issue. I can tell you 50% of these things is technology, 50% is discussion with lawyers. Yeah. We also monitoring, as you can see in the right lower corner, we are monitoring the satisfaction of the customers. We are also monitoring the deviations from the set point, and we are also looking to the load ratio of the equipment and what we can do for demand management. So this is combined with energy storage, and this is most important for this region as you have a lot of PV panels, but you also have a lot of islands in the region. And the islands are not so well connected to the mainland for the power supply, so this is even more important for them. So what is now the recommendation based on our experience towards the policymakers? So first of all, we have to understand how investments are made. Investments are made based on decisions made during the design phase of the building, including the cost of the building, the construction, but also the maintenance cost. And therefore, the energy performance calculations are so important. It's crucial for the decision making. If you have a technology that is reducing the energy consumption, but in the calculation this is not reflected, this is the first one they scratch because it costs money and it doesn't make any difference in the calculation. In the reality, yes, but in the calculation, no. So this is most important. Innovations have to be valorized in the calculation methodology. And this is crucial for energy performance of buildings. Be careful with setting standards and regulations for these calculations. A unified European calculation is needed to assure the most economical solutions for innovations. That's the scale effect. If we would like to go to a reduced energy consumption, we have to unify the requirements. This can be valid for, this is here Europe, but can be as valid for the Mediterranean region. And we have, as I said, to include the innovation into the calculation, like inverter technology, demand management, energy monitoring and management systems. They should be included. And national approaches may not lead to the most energy efficient solution or the most energy efficient path. So to come back to this hurdle race towards the NZEP ratings. So what's so important about this NZEP and what has changed? So up to now, we were speaking mostly about hurdle 1 and 2, and this means that we have the buildings, the shell, and the technical installation, and in this period, we speak about the payback of the energy recovery measures as a key. So if you have an energy saving, what's your payback? How many years does it take? Well, it is changing with the NZEP because you have to compensate your non-renewable energy by renewable energy to come in the balance. This means you have to invest in PV panels, windmills, etc. So any energy saving you are doing, or any renewable energy you are using instead of non-renewable, is a reduction in the payment for this last step. So it's changing the economical mechanism because your payback is not any more years, it's instantaneously. It's coming there immediately. But it also clarifies that it doesn't make sense to make energy efficiency requirements that have a longer payback than the payback for PV or wind. So it means this payback is something like 7 to 8 years, PV and wind, sometimes 5 years. Well, it will not go in the balance with this if the energy requirements are too costly. And we should not forget something, indoor air quality and indoor environment quality. Yep, some people said already, yes, in the northern they do this ventilation, mechanical ventilation, because they don't want to open the window. And no, they do ventilation for the health. Otherwise they get mold and they get sick buildings, etc. So if you look to indoor air quality, what is this? Temperature, humidity, pollutants. If we look further to indoor environment quality, you have light, space in the building, sound of HVAC, but sound of other devices, and visual comfort. If we look in our HVAC, we are confronted with temperature, humidity, pollutants, and the sound of HVAC. And we have to understand that for the people, what is most important today? First priority is safety. Second priority is health, then comfort, and I think energy is coming quite later. The first priority after comfort is the holidays and then the energy. Yep. This one, the next one I will skip because you have heard too much about why it is important. But if we look to the landscape in Europe, what is used as ventilation? Well, air handling units are typically mid-Europe on the eastern side and on the middle side of Europe, I mean, and Italy has also air handling units, except in residential. In the northern part, we have heat recovery and energy recovery systems. And in typically southern parts, mostly, but even in the UK, we have just single exhaust fans, because that's the regulation. And it's so depending on the local regulation. I can show you here, that's just an extract of regulations in different countries about ventilation. I can tell you there are 35 different regulations in Europe about ventilation, 35. I cannot imagine that there are 35 different impacts on the people from the climate. But this is negative for the innovation. There are too many differences. Some people are asking 18 square meters per person, and some others are asking 45. Why? We don't know. But it's from the history. These things are not made at the same time. They are made at a different timing with different people around the table. So that's the background why we come to all these things. If we look then to some technologies like heat recovery in new dwellings, well, it is not mandatory in a lot of buildings. Even Germany does not ask it. Today in Germany, you can ventilation in a residential building, a window that you can open is sufficient in Germany. Yeah? For the future, it may change. So we can see that heat recovery is more in the northern part, and the southern part, we still don't see it. But this is as important, not for the heating to recover, but for the cold to recover. And you have to look not only to the sensible heat, you have to look also to the latent heat. Very important for this region here. So what are our further steps that we require? Oops. Yeah, okay. So according to the EPBD, minimum energy performance requirements shall take into account general indoor climate conditions in order to avoid possible negative aspects such as inadequate ventilation. This was already in the directive in 2010. And the new directive that will come this year, it's even more stressed, this indoor environment quality. So we have some challenges, and we have to make sure that we make the proper rules for this, taking into account what is the focus on the climate zones. How shall we connect, How shall we connect the indoor air quality with energy efficiency? First of all, we shall optimize the exhaust of the conditioned air to avoid overventilation. So optimize purification before ventilation from the outside. A lot of cities where the outdoor air quality is also not so good. So purification may become a very important factor. Not only for the indoor air quality because of the bad outdoor air, but also for energy saving. And where you really need outdoor air, optimize the control and function of the indoor air quality. Use sensors, use controls to give a good indoor air quality and to minimize the ventilation. The most energy efficient ventilation is the ventilation that doesn't need to run. So, not that it is not required, but we have to minimize it. Where outdoor air can improve the indoor air quality and give low energy requirements, use the outdoor air. use it. If you have cold air available with a good wet bulb temperature, just use it. So the unification will lead to a higher indoor air quality and a better performance. That's very important, that you unify your requirements. Because the unification for the region means better optimized products as a total. And surely recognize new technologies and the new calculation methods. And that's more than ever valid for ventilation. So what else can we do in the short term? So first of all, we should provide more efficient equipment, and we should assure that the technologies which are there are protected. So we went with the refrigerant, for example, from CFCs to HFCs, then we went away from HFCs for the ozone layer, then we got high GWP HFCs, and now we go to low GWP refrigerants for use and equipment. And you have seen, those who were in Mostra Convenio, for example, you all have seen that for Dieryckx systems, we are going directly to a refrigerant called R32 in order to drastically reduce the impact of the refrigerant on the climate. It's around going down with 75%. And yes, maybe in the far future, there may be other technologies coming, but we don't have the time for that. The sooner, the better. We have to act quickly on these things to reduce the CO2 emissions. What can we do more? I will repeat it. It's make common calculations. Don't stick with national situations. Recognize the technologies. Recognize demand management. Recognize air purifications. And also the use of high efficiency technologies is most important, but also the proper sizing of the equipment and the building. It's a benefit for both. It's a benefit for the resource, but it's also a benefit for the energy efficiency. And proper installation and inspection, extremely important. But also extremely important is recovery and reuse at the end of the life of the equipment. When we abolish buildings, when we take away equipment, this recovery and the reuse is essential, but because I tell you the resources are going to be a problem within 10, 15 years from here. So we have to assure that we also do these actions. So to repeat, the challenges, like I said, the big challenge is effective use of energy, not only efficient equipment, but effective use, like demand response management, improved air quality, so developing an indoor air quality metric, health and comfort, keeping it in balance with the energy efficiency, sustainable cooling and energy storage, advanced tools for energy performance calculations, and BIM modeling. I heard the name already here around. BIM modeling is becoming more important. Today it's for the size, but in the future it is just to calculate the building performance. You put your models in your system, you draw in the drawing table, and they calculate the performance. That's coming. Standards and legislation as a stimulus for the new technologies. So when you make rules or standards, you have to emphasize on the technology-neutral requirements. And where it is not possible, you have to integrate a fast update on innovations. And where possible, I repeat, to include European or ISO standards to reach cost-effective standardization process. Making standards is not cheap for a country. So if you can use a global platform, use it. If you have any questions about using standards or using platforms, I can help you in order to get integrated into the system. Also, Riva can do, and the association can do. Thank you very much.
Thank you, Martin, for sharing your experience with us. Maybe if we have time for one or two questions. Yes, please.
Thank you. for the presentation. I may say that I agree very much with you, mostly in what concerns, let us say, the standards and the regulation in Europe. I think that the worst thing is what we call the politically convenient, because we are always producing standards where there is a place to the national regulations. So, for instance, the sand standards that we have nowadays regarding the EPBD, they come with two annexes. So one annex with the proposed values and another annex to the national values. And okay, this way I think it would be difficult to have a common framework in Europe for this issue of the energy performance of buildings. So keep on with your fight against this, let us say, extreme diversity in the national regulations. Because it also happens with the certification, because any country has a different certification scheme. And for instance, an apartment, if we are calculating the area using the different systems in Europe, we may have a change about 25%, because we may consider the thickness of the walls, or we may not consider, we may consider the balconies and so on. And after, when we come to an indicator that is divided by the area, we will have, let us say, completely different values, depending on the country.
I'd like to give you an answer on this. For me, it's not a fight against this. I'm very happy that today they made the European standard and that every country can make an annex with a deviation. That's most important. In 1973, they made the electrical standards for safety of household equipment. The standard was a number of pages, but the annexes with the deviation in each country was 3 times higher than the standard. But 15 years later, there was a standard which was mainly a unified standard, and there were 6 pages only of deviations. Today, there are almost no deviations anymore. So the step that we are taking to make the standard, adding the deviations and the annex, is crucial, because this will come to the fact that we get knowledge about the deviation in each country. It also creates the opportunity to try to unify the requirements. This step is essential. It's an essential step. Trying to move everything and saying now you have to do from this to this is not feasible. And the history has shown this with other standards. So I'm not skeptic. I'm very optimistic for within 15 years. I will be retired, but it doesn't matter. Okay.
Okay. I have to thank you, Martin, because we have to stick to the schedule. You may discuss during the coffee break on these general topics. I think it's an important topic for us. Thanks a lot. So, Professor Horuz, you have the floor.
Okay, thank you. Good afternoon, ladies and gentlemen. I know that you are tired, and I know that everybody has different backgrounds, so I will try to explain 4 different systems, but I will try to make it as easy as possible. Otherwise, I will lose you. Most of you have already gone. So the topic is absorption heat transformer driven double effect absorption air condition. The electricity is generated from the fossil fuels. And we know that there are too many problems, okay? Everybody has fear that in the near future we will have too many problems about energy. Okay, so this forces people, especially engineers, to try to find different types of fuels, okay? So renewable energy or different types of fuels that we can produce electricity with. So as far as the air conditioning is concerned, buildings is consuming a lot of energy, right? And why? Because mainly it uses vapor compression refrigeration system. So as you can see from the name, compressing vapor. So compressing vapor is very expensive. You need to give a lot of energy. You turn everything off in your home, but you can't turn your refrigerator off. You will see that your electric meter is running. Why? Because compressing vapor is expensive. So you are compressing vapor in your refrigerator, okay? So it will be the same when you are using your AC for your air conditioning, okay? So this is the main reason compressing vapor is expensive. Okay, what are the alternatives? One of the alternatives may be the absorption refrigeration system. As Martin said, they did some experiments, but absorption refrigeration system is not quite popular, and the payback period is quite low, quite high. Why? Because if you compare the COP of the vapor compression refrigeration system and absorption refrigeration system, the COP of the vapor compression refrigeration system is about 2.53. If you use water or soil, you will get more, of course. But as far as the air is concerned, air-cooled vapor compression refrigeration system COP is about 2.5 or 3, okay? But if you check the COP of the absorption refrigeration system or absorption air conditioner, if you are using ammonia water as a solution, the COP is about 0.5. If you are using lithium bromide water, the COP is around 0.7. So how can you compare with the 2.5? But if there is a waste heat available, if natural gas prices is reasonable, if there is enough solar energy capacity available, okay, so you can use absorption air conditioners. But I will try to explain what the absorption air conditioner is, starting with the single effect. The COP level is low. So the main topic of this research is try to show you how you can increase this COP level. Okay? So let's start with the single effect absorption air conditioner. As you can see from these schematics, the condenser and the evaporator side is exactly the same with the vapor compression refrigeration system. The only difference is that we don't have any compressor, so we don't need to compress vapor. Okay? So we have heat exchanger group. Okay. First, let me explain what absorption is. Let's say you want to drink a cup of tea. Okay? I want with sugar. Okay. When I put sugar in it, when I stir it, what will happen? Can you see the sugar in it? No. The tea is absorbed sugar. So you can't see any sugar in it. You put second one, the third one, everything will be absorbed up to a certain level, of course. Okay. How will you take the sugar out? I know you are tired, but you know this. So when you heat it, since the boiling temperature of water is lower than sugar, when you heat it, okay, if it is the atmospheric pressure, around 100 degrees C, all the vapor, all the water will be evaporated. You will have sugar at the bottom. So this system uses this technology. We have sweet tea in the absorber. Okay, we pump it. Okay, this is the liquid pump. It consumes really a small amount of energy. Okay, we pump it to a generator. Please don't pay attention to the solution heat exchanger right now. We pump it to the generator using waste heat, using solar energy, okay, using any type of heat that is already lying around. When you heat it, you will take some water vapor out. But we don't take all the water out. Otherwise, if we take it, the sugar will be crystallized. It will be in the crystal, in the solid phase. We don't want that. We want every part in the liquid phase. Okay? So what will happen? We will take some water out. It will be condensed. And then we will send to the evaporator. We will reduce the pressure. The temperature will go down. It will take heat from environment to the room that we are going to air condition. So it will be in the vapor phase. It will come back to absorber. The more sweeter tea will come back to the absorber. The absorption process will take part again. So this is how it works. I was not joking when I said tea and sugar. This is one of the solutions that we use in absorption refrigeration system or absorption air conditioner. Salt and water. Any type, on any two types of materials, when you mix, if one absorbs the other, and when you heat it, the boiling point of one of them is lower than the other one, and if you can evaporate easily, that's the one we can use. There are more than 200 solutions that we use in this type of systems. But mainly ammonia water and lithium bromide water are quite popular solutions. Okay? When you use ammonia water, the COP value is around 0.5. When you use lithium bromide water, the COP is 0.7. Of course, everybody uses lithium bromide water. Why? Because, look, we are talking about 0.5, 0.7. It means that 50% more efficient than the other one. Okay, 0.7 is small, but 50% higher than the other one. So most of the producers produce ammonia air conditioners with lithium bromide water. There are some advantages and disadvantages, of course, but this is the commonly used. Okay, so if you run this system, this is how you can determine the capacities. This is the crystallization restriction for the lithium bromide. Why? Lithium bromide is a salt.
To cut.
Okay, so you need to pay attention on the crystallization. So these are the equations that you can find the COP values, and this is the graph that shows the COP versus the generator temperature. If your waste heat source temperature is getting bigger, you will get higher COPs. Okay? But up to some certain level. No matter how hot your waste heat source temperature is, you are not getting anything more than 0.78 something. Okay, I have higher source, waste heat source temperature. No matter how hot you have, this is the limitation you have. So at this point, double effect absorption systems are coming to the market. So the schematics of the double effect is like that. It may seem a little bit complicated, but it's not. Please pay attention here. So you have two condensers and two generators. Okay? But as you know that condensers give heat out. And at the generator, in order to evaporate the water, we need to give heat. So we take heat from the condenser, high temperature condenser, to heat the low temperature condenser. So there are two extra heat exchangers, but we don't worry about it because the one is supplying the other one. We don't need to give any energy to that, to extra two heat exchangers. So we give energy to the high temperature generator and we take the cooling effect from the evaporator. Okay, this is the double effect. Why? Why do we need this double effect? The efficiency or the COP value is going above 1. See, from 0.7 we go to 1 or 1.4. If you play with it, you go to 1.4. Okay, so if you compare the single effect COP and the double effect COP, and this is the Carnot COP, so you can see that with the double effect, you get better performance. But if you have higher level of waste heat source temperature, Okay? So at this point, the aim of this project, of this paper, is coming to the market. We thought if you have low level of heat source, but if you have low level of heat source, you need to use single effect. You can't use the double effect because you need to have higher level of waste heat. Okay? So at this point, a new system is coming. It's called absorption heat transformers. How does this system work? It is exactly the same system, but instead of running condenser and generator at the high pressure, we run them at the low pressure. And on the other hand, evaporator and absorber run on the higher pressure. Why? Why? During the absorption process, the heat occurs. We need to take that heat out. Okay, this is the key point. If you use this heat, you can generate higher than your waste heat source temperature. You heard correct, yes. Let's say you are feeding the generator and evaporator for the 90 degrees C. Your heat source temperature is about 90 degrees C. You can get at the absorber at 120 degrees C or 150 degrees C. With the double effect, 160 degrees C. You see, it's different than the classical waste heat utilization systems. The input is 90 degrees C, the output is 120. So you may have 50 degrees lift. Okay, so we applied this to a company. The company had 4 different units. Each produced 50 tons per hour water at 90 degrees C. Okay, and they were requiring a steam to run another company. Okay, yeah, another company, another machine requiring 120 degrees C. We used this system and produced from 90 degrees C, we produce 120 degrees C steam. And using this, we run that machine. And with this paper, we got more than 60 citations. Okay, so we applied this to here. As you can see, this is the heat source from the company. We used absorption heat transformer to generate, to lift 90 degrees C to the 120 degrees C. From that, we get higher COPs and higher cooling effects.
Could you come
As
to
you
conclusion,
can see,
please?
yes, thank you. Here, this is the COP comparison, and this is the cooling effect comparison. So what I am saying is that there are possibilities, okay? Don't throw absorption system away.
Sure.
There are still some process that you can apply and get good results. Thank you very much.
Thank you very much. We have time for a very short question, if any. Yes, please.
Thank you, Professor Horuz. I want to, do you know the systems who works in absorption system in Turkey? And second question is, the construction company is absorption or generator. I know Yazaki and Enesu. You know another
Yes.
in the world.
Thank you.
Thank you.
Thank you.
Thank you very much.
Yeah. I know that there are some hotels use these systems, but the point is that you are the designers. You don't know this system, so if you don't design the system using this, it will not be seen in the future, okay? And even the manufacturers believe that this is not a good system. So how do you expect to see more than that? Okay? There are different companies. Rubor, Arkla Rubor, okay, he asked the companies, that's why. Okay, sorry, thank you.
Thank you. So, thank you, Professor. Çankaya University
Çankaya,
in
God
Ankara,
bless you.
excuse me. And Timuçin is an assistant professor in this university. So you have the floor.
Yeah, thank you very much. Good afternoon, ladies and gentlemen. I'm Timuçin Harputlugil from Çankaya University. I'm an assistant professor, doctor in Department of Architecture. Today, I'm going to make you a presentation titled Through a New Generation of Energy Performance Certification Systems. As I have limited time, 12 minutes, 12 slides sharp, so I will try to go in brief and try to tell you the conceptual framework of the system. Whenever we go to the background of the system, just we know that the EPC systems are just designed with the EPC systems are designed based on the EPD regulations, and just the aim is just to get the data, to raise the awareness, and just maybe if I can get it closer, just I can say it.
Be careful, you're missing.
To find green nodes. And the other thing is that the difference is that we have several EPC systems, and the difference is the methodologies and their assumptions and their rating systems are just based on the several systems. So to go on further with this, I can say you that the EPC systems, the content of the EPC systems with related to EPD, we have the EPC systems to go on further. I mean that as we know that the EPBD regulations are just for us, EPBD systems are offering us for new regulations based on net zero and nearly zero buildings. We are getting data for them with these EPC systems. So I will try to show you some examples from the countries of EU, the EPC systems. As far as I know, more than 30 systems are used in European countries in the EU Union umbrella. And the problem is that they are using different approach, different methodologies, and different units. So it's not so easy to arrange, or it's not so easy to correlate the outcomes of this data under the umbrella of EU. And what I can say you is that I will try to tell you about this Turkish system. This is the second upgraded version revealed in the last quarter of 2017. As you may see, the EPC systems are just providing us data about the energy performance level, green gas emissions, renewable energy usage, and energy consumptions related with this, related with these topics. So I would like to tell you more about these limitations. So the problem is that there are too many variances of these EPC systems in European Union countries. You see that it's really so hard to correlate the outcomes of this data and just to provide more knowledge related with these nearly zero or net zero energy systems. The thing is that maybe you noticed that there's most occupant behavior is not included. The thing is that the occupant behavior is only analyzed in the methodologies with the simulation part. But the thing is, you didn't see that any part in the EPC certificates that's including the user profiles, I mean the occupant behavior profiles. And the thing is that when you get this EPC, it's a static data, not the dynamic. The thing is with the time change, the data doesn't change. So the thing is we know that most of the EPC systems are just lasting for 10 years, mostly. The thing is that whenever you get the data, for the next 10 years, you will not be able to get an extra data. And the other problem is that all the EPC systems are in the building scale, and they don't cover district, neighborhood, or urban scale. So the problem is that we know that the buildings that we live in interact also with each other with the energy consumption. So this current EPC systems has limitations also in this area. And others, as I already mentioned, the data gathering and the quality is also limited. And another problem is that data updating protocols are also limited. What I try to mean is that Turkey, for example, if we give, for instance, we give Turkey as an example, the Turkey just upgraded its version 5 or 6 months ago. So the thing is, the earlier protocol that were used to get the data is not possible to be used in the new system. So we have a huge data we gathered, but it's not so easy to transfer this data to the new system. So whenever a new system is needed, it's impossible to get the back of the data that we had earlier. So I would like to show you a picture. You know that maybe you're so familiar with this picture. A few days ago, Mark Zuckerberg, the founder of Facebook, this is a picture of him before his testimony in the US Congress. He was, he was called to the US Congress because of providing user profiles to third parties for to be analyzed. You know that a company which he transferred to the user profiles is being said that can make projections of the US voters based on their likes. I mean that if they analyze an interactive 65 likes of them, they can make a projection with 85% accurate the parties that they are going to vote. So it's interesting that, and also in the world, the user profiles are getting so important. Sorry. So what I try to mean is that we the designers, as I'm an architect, as you all are the architects and engineers, we all design not for the energy, we design for the occupants. I mean the people, I mean the humans. So the thing is, what we are designing is we just try to raise the awareness or try to raise the quality and comfort of the indoor environment for humans. And the thing is, energy is an important thing, but we use energy to make it. So the problem is that we shouldn't get stuck into the fetish of energy when we are designing. So we should be also caring about occupant behavior, but when I say occupant behavior, it's mostly just like people just understand it with the numbers and just any numbers we use in simulations. But to be honest, it is not, because the human behavior, I mean the occupant behavior, is so changeable. For example, think of yourself. You are living in the buildings that are energy labeled. Your houses, your office buildings, your schools, your hospitals, whatever. But the thing is, you are not labeled. But also, you act and you consume the energy, not the buildings. So the thing is, but think that you act differently in different places. I mean, you are at your home, you act differently. At the office, you act differently. Here, you act differently. So the thing is, and also, this is also changeable. So what we need is, when we are analyzing occupant behavior, we don't need a static data or just simulation data. We need real-time data. So what I would like to come to is just this dynamic data. How can we make it? On my left-hand side, yes, on the right-hand side, sorry. It's on the right-hand side, just you see an energy analysis based on the solar power. So the thing is, what I try to mean here is that the buildings are affected too much with themselves. So there's an interaction. And whenever you make a static EPC application, and when you get the data, on the left-hand side, you see that a new building is constructed. I think it's an urban regeneration area in Istanbul. So that, do you see the other buildings affected by the shadow of it? So if they had the EPCs last year, so from now on for the next 10 years, their EPCs are not working very well. So the thing is, what I try to mean is that we need a dynamic system. And what I try to come on, with the new generation, I try to mean that for EPC systems, we should adapt it from a certification system to a real-time data analyzing system. And this should be, I think, can be made with creating a plug-in system to the smart systems. What I try to mean is that as we can make, and if we can have the interactive data of the buildings based on occupants and transfer this knowledge to a general system, then we can also produce energy very efficiently, and we can use it very efficiently also. So, as a conclusion, what I can say is that from now on, I think we should be thinking that the EPC systems are not only static certification systems, they should be the plugins that we can put to the smart systems based on occupant behavior, based on smart system focusing, based on integration and interactive systems. And we shouldn't forget that these systems should be dynamic and always should be making more data that we can analyze and we can put forward for energy efficiency. So, as I said, finally, the aim should be, in my opinion, from now on, thinking of EPC as a plugin for smart systems. So, that's my speech. Thank you very much for your attention. If you have, thank you very much. If you have any questions or comments, I would be glad to hear that. Thank you very much.
Thank you for this smart presentation. Is there any question? We have some time for one or two questions about the trends. I think it's very interesting. No comment? Manuel? Yes, please.
So I can have you.
Just a question, how to harmonize the data?
The data, yeah.
Yeah.
No, how to harmonize?
How to harmonize, yeah.
Yeah,
The
because
thing-
it's, of course, first there is another problem, how to collect all the data and to have a reliable system, because when we are transmitting data, how to deal with data losses and how to harmonize.
Now, thank you for the question. The thing is that we are still working on this. As I said, this is a new project that we are working on it. It's a recently begun project. So this is just like introduction, just telling the conceptual framework. The next step is just, I think we mentioned the methodology, but the thing is, it's not, I think we need time to reveal it, to make it. But thank you for your question, but we're still working on it.
Thank you. Any other question? So I have to thank you for your attendance and thank the speakers for their very nice presentation. And I close this session. Thank you.
I'm first of all going to give a little off-topic plug here for the International Building Performance Simulation Association, which is a group that promotes simulation. We have building modeling of all sorts. We have about 38 regional affiliates, including ABIPSA Turkey, which has a little stand out here. And Gülsu will happily accept your questions about it. But we put on conferences, the Building Simulation Series, which is about to have its 16th iteration. We have a journal, 2 books with our name on them, and you can learn about us on the web at abipsa.org. But my talk's about something else. That was just because I'm president of ABIPSA and I'm trying to inform the world of how wonderful it is. So, all right, what I'm going to talk about is equipment performance data. And as anyone who's attempted to do detailed simulation knows that getting good equipment characteristics is a very fraught issue. You need data for the full range of operating conditions and for part load conditions to get accurate simulation, and especially as envelopes get bigger, better and better, the characteristics of the HVAC system become a dominant factor in overall performance. All right, and one of my major points is that ratings just don't do the job. They don't provide sufficient information. So I'm going to talk about ratings and just enumerate some things that are wrong with them, and talk about the performance data availability, and then the development of consensus standards for overcoming these problems, and a few recommendations. So the context of this is basically full year, hourly, or shorter time step simulation that is classically done by applications like DO2, Energy Plus, Trinsis, models of that sort that are used widely in both compliance applications and design analysis. All right, so ratings, just to state the obvious, are a few or a single value that characterize the performance of something. So it'll be like an energy efficiency characterization. A couple of US examples are, we have a rating called HSPF, the Heating Seasonal Performance Factor, which is for an air source heat pump. And so it's essentially an annualized COP. And then there's IEER, is the Integrated Energy Efficiency Ratio, which is used for chillers, and it's evaluated at several different points. Now, these provide good general guidance of performance overall, and you can vaguely say that if a higher rating is higher efficiency, and that's good. But these ratings were developed for the consumer market and simple evaluation, and basically they have limited use, no matter how tempting they seem, they have limited use for simulation. So just a few of the things that are wrong with ratings from our point of view. And there's nothing wrong with the ratings, they're just not fit to our application, to the modeling application. So this text here says something about round off, and it says that when you publish, the data shall be expressed in multiples of 0.05, and I apologize for the IP units, but there you go, or multiples of 0.1 for IEER. And then in other cases, part of the rating derivation process will have stepped values in it. So if you tried to reverse engineer it, you're up against, you can't figure out what the actual original input was. Another issue is auxiliaries. One of the reasons you use detailed simulation is that under your conditions, you want to know what's going to happen. There's situations in mild climates where the crankcase heater in an air source heat pump can use more energy than the compressor over a year, because in the mild climate, it heats 100 hours a year, and the rest of the time the heater's running. And so you'll never see that in because you get a rating, somewhere in that there's accounting for some amount of crankcase heater, but you don't know what it is, and you can't extract it to analyze it for a different load mix. So, but the biggest bugaboo is ratings aren't unique. In other words, two pieces of equipment with the same rating do not necessarily operate the same way over a range of conditions. So again, if you're trying to optimize a project for your specific climate, the rating just doesn't give you enough information to choose between different pieces of equipment. So one of the things for regulation uses, a very common scheme in the US is performance-based simulation, where you run your project against a reference project. The difficulty is that often regulators will state the requirement for the reference project as a rating. You shall have an HSPF heat pump of such and such, but you're actually going to run that in a simulation as your reference for the comparison for code compliance. So what heat pump do you run? Because all you know is this one number. So, so defining reference equipment is actually quite hard, because you have to choose what you think is a representative good level of efficiency, and it's really not a recognized task, and it's pretty hard. So I'm not going to dwell on that, but just point it out. So, so then you say, okay, well, the ratings, there was some test data that went into those ratings. So suppose we could just get those test results. And that's helpful, but it isn't sufficient. And so, for instance, the tests for air source heat pumps, in the US at least, there's a couple of rating points. But if you do a linear extrapolation through those rating points, you can get crazy results. So really, the test points are designed to feed the ratings, which are not designed for us, again. So, all right, so what do models actually need for equipment data? And a very common scheme that's been in use for decades is the correlation method, AKA curves, where in DOE2 Energy Plus, there's a biquadratic or some other polynomial curve fit that tries to represent the performance in a bunch of dimensions for the model. Other applications, Trinzis, Energy Plus, ESPR, will use performance maps, where you just have tables of various independent variables and the performance at those points. So to develop specific data for a specific project, for a large project, you'll probably have the resources to get performance maps, reformat them as needed to fit curves to them or feed them properly into Energy Plus, say, and because you have the time to put some effort into reformatting data. For small projects, people just use defaults. There's no time to mess around, and which is a limitation. So a typical performance map, this is, again, residential equipment from the US, IP units. Again, I apologize. But this is what you get as a PDF. And you say, okay, now I want to make this into some kind of comma-separated file or do something or other with it and read it into this program or that program. It's a bunch of work. I mean, it's not horrible, but it's going to take a while. And if you're doing quick projects, it's impractical. So worse than that is, even if you can digest that thing, if you wanted to use different applications, they have different input formats. So you'd have to do it again. And there are ever more tools, ever more analytical methods that are coming out, and there are new codes, asset ratings, LEED, Standard 90. So a more productive workflow is really important. So one question is, why is this data not available in more convenient formats? And we, our modelers, basically in the ASHRAE committees and ABIPSA committees and things, we sit around and bemoan the fact that nobody will give us the data we want, and then we all, say the world is unfair and go home. And upon reflection, it was sort of began to think about why, we never really asked for what we want. It's just like, you should give us the right data, and that's all I'm going to say. And that isn't a productive point of view. So a lot of the barriers are that the manufacturers don't understand what we want in many cases. They don't understand the simulation application. They don't know in detail what they need to provide. Manufacturers have resource limitations. They're not going to spend a whole lot of time developing data formats and export procedures and whatever. In some cases, manufacturers just don't know how the equipment performs except at the rated conditions, because it has this rated thing and the control system will take care of the rest. And then finally, manufacturers often have proprietary concerns, so they don't want to publish the data. Well, so what we finally realized is that we need a standard. And the ASHRAE standards process is very good for this kind of issue. And what you do is you convene the stakeholders. ASHRAE, if you do an ASHRAE standard, you have to have representatives on your committee of all impacted parties, basically. So you get data publishers, who are the manufacturers, you get software developers, you get other related professional organizations, and you get software users, engineers, and design consultants, and you form a committee. And then you work together, and by consensus, you agree on data formats. And then the big sort of deal is the publishers of the data, the manufacturers, agree to write data in that format on the basis of the understanding that they'll only have to write one format. And then the software developers agree to implement the ability to read that format. So everybody has to do some work, but at least it's a common setup. All right, and then the goal is you get automated import of this data into the modeling tools, not untouched by human hands. So this is what we've done. We've made standard representation of performance simulation data for HVAC&R and other facility equipment. This is a draft standard. Well, it's a very early draft at the moment, but we have got some stuff on paper. And I won't read this, but basically what the purpose and scope of the standard are to facilitate sharing equipment characteristics, and then our scope is essentially anything. We wrote it that any facility equipment we're allowed to, we can deal with that. So initially, we decided, I'll get to that in a minute, but anyway, so the way you can standardize data, equipment performance data in our realm, there's a number of approaches that one could use. You could use performance maps, which is just data, essentially. You can do coefficients, so you could actually make the DOE2 or the Energy Plus curves, and you publish the 12 coefficients or whatever it is, that you make the manufacturer fit those curves, and then here's the ABC numbers, the coefficients. Or another one we thought of would be so-called active elements, where you essentially define an interface, and then the data publisher could produce a DLL or an FMU unit, some machinery, software machinery that could be accessed by a data model. So we use the term representation because we don't want to be constrained to any particular approach. But what we decided for our first effort in Standard 205 was we would use performance maps. And so all you have to do to make a standard is you get 20 people around the table and you agree on the names of the variables, their units, their definitions, their units, and their precision, and a number of other things about their validity tests and other things like that. And so we structured our effort that we had a body of the standard, which is common requirements and definitions, naming conventions, units, and that sort of thing. And then we plan an endless series of appendices, which are called representation specifications, which cover specific components. And there are 3 of them in the first draft, which are liquid-cooled chillers, unitary cooling air conditioning equipment, and fan assembly. And 6 years we've been at it to put that together. It's amazingly time-consuming. Everybody says, oh, why don't you just figure out a common thing and we'll all go home? It is very hard. And it's what's amazing is having the manufacturers at the table with the software developers, how much each side does not know about the other one is very instructive. So it's been a great experience, even if slow. All right, so for our names, for instance, long discussion about how to name things. Well, we decided to use long, at least somewhat long names that are self-documenting. So we'd have a variable name called like air volume flow rate. Well, we could have called it AVF, but we decided no, we'd use a long name. And that maybe is going to make the files a little bigger to the extent they contain the names, but we decided the clarity was worth the space. Units. Being the United States, we had a big issue about whether IP units would be supported. And ASHRAE's policy is dual units. But one committee member said, if you have 2 clocks, you never know what time it is. So we said, okay, we got to do 1 set of units that'll have the burden of actually publishing the data. And if you're going to do 1 set of units, it's got to be SI. So that's it, SI only. That's what we decided. And so each of these things took, hours of discussion. And there's a pretty large list of them. All right, so the representation specification is a human-readable PDF document that defines what is in a given representation. So it tells the data publisher how to write the data, and it tells the application developer, the software, the model developer, how to read the data. I mean, what the format is and what the variables mean precisely. And for users, it's to be able to clearly understand what the data is. So in each one of these things, as I said, there are 3 of them initially. Generally speaking, we have a device diagram that is shown here for a unitary air conditioner. And we have a diagram that shows what the component is, kind of how it's represented, at least from a software point of view, the data element definitions, the validation rules. So we spend a lot of time on validation that basically you can have simple validation, just, you know, this value must be between this and this, or it's just, you know, not acceptable. You know, airflows have to be 0 or greater, that sort of thing. But then they're interpoint, well, within point definitions. For instance, the air state leaving a device has to have humidity greater than 0. And actually, somebody involved in the committee early in the effort did some analysis of published data from manufacturers, and there are a whole lot of points in that data that were off the edge of the psychrometric chart. They're, you know, they're below, well, either hypersaturated, oversaturated, or undersaturated. So anyway, so we've defined rules that, okay, this has to be physically possible, et cetera. Then there'll be references and supporting information that describes more, provides background of what we're doing. So that's a human readable document. And then the representation itself is a file, and that will have a lot of specific information that follows the representation specification, but it's in a specific file format. And it will be including the identification information and then all the different performance points. And then there'll be ways of indicating that certain points you can't actually operate under those conditions. So there's a lot of concern from the chiller manufacturers about you know, what's going to happen under unloading conditions, what's going to happen under this or that, and we had to struggle with ways of conveying that so the software didn't, so the modeling software doesn't go ahead and say this chiller is going to produce, you know, it's going to be wonderful, but in actuality it wouldn't run under those conditions. So there's a lot of issues that we've had to grapple with. They're good faith errors that what you think about is you know, they're typos, they're bugs, that sort of thing. So our response is these validity rules, as I said, is that we provide ways of testing for those things. There's bad faith errors. What if people want to put out counterfeit data? So our response to that is that the standard says if you want to encrypt the data, use digital signatures, any other thing like that, you go ahead. And the same is true for proprietary data. So we're just saying this is the format. If for your business purposes you want to keep the data private, you can find any number of encryption facilities to use to keep the data hidden and only give it to a certain customer. That's fine with us, but it's not our purview in the standard to do that. The implementation is, so we're experimenting. See, the heart of this thing is the definitions of the data. The file formats and the actual how a file is written will come and go as XML or JSON or YAML or all these other schemes go in and out of fashion. But at the moment, we are experimenting with a thing called flat buffers, which there's a link there. It's a Google thing, and it's designed for conveying binary data quickly. It's actually, I think, for the game industry primarily. It's designed to convey binary data over the internet quickly. And that's actually our problem, is that you want to take a whole bunch of data that describes a piece of equipment, and as a user of one of these programs, you could download it, plug it into your thing, and go. And so anyway, that seems to be a good, so we're doing some experimental coding right now with this. And then we're using open source libraries to some degree, but we're developing an interpolation library. You end up having, if you have performance maps for a chiller, there are 5 dimensions, I believe we cover, so you end up having to do 5D interpolation among the points to get the actual performance at a given point. So the status of this effort is we have completed an advisory public review, which is an ASHRAE process where you just solicit comments. People make comments and they're not binding or anything, and we are digesting those right now. Many of the comments were very helpful, and we're incorporating that into the draft, and we hope to vote it out for a full public review draft this in June, when our next full meeting is. And then we'll see how the uptake is to see if people use it. And we've started talking about additional components such as VRF equipment, cooling towers, fan coils, heat pumps, water heaters, windows, a lot of other things. Once we have the scheme working, it's, at least for some equipment, it's quite, for instance, fan coils and cooling towers, we believe, will be fairly straightforward to do. VRF is complicated, water heaters are complicated, storage water heaters are complicated because they have state. They, you know, what they do right now depends a lot on what happened 12 hours ago. So anyone interested in participating in this, we would welcome the efforts. All right, so a few recommendations. First of all, just make it clear, and any of you are on committees and related to these things, that ratings, depending on what the target is, ratings are not sufficient. They're fine, but they're not sufficient. And reference equipment is needed for if there are efficiency requirements in standards, in regulations, for instance. So then keep going with this kind of standard that try to get this nailed down so that basically we can pass data around among manufacturers and software users efficiently and accurately. It may be that some other standard carries the day and not this one, but we'll see. I think international harmonization is very helpful so that it's, again, there aren't different schemes in operation in different places. And keep a lot of this, as much as possible, open source so we can all share it and help develop it. And also prepare, one of the things, I didn't really talk about this, but many of the underlying standards, including ASHRAEs, are expensive. And you know, you can spend, I don't know, $85 and end up with a 15-page document that really isn't that interesting. And I think it doesn't help if we can't all see the standards easily and thus criticize them and develop them. And then finally, one last bit of shameless ABIPSA promotion here. The next building simulation conference, which we hold this every 2 years, is the 2nd to the 4th of September 2019, a year from this fall. And it will be in Rome, so that's convenient for many people here. The call for abstracts will be out soon. And ABIPSA Turkey and others will be publicizing it, and I encourage you to submit abstracts. These conferences have been very successful and enjoyable because there are people there from all over the world. So there's several people here who will be involved also. So come talk to us if you're interested. So thank you very much.
I'm sorry, but I forget to say that Mr. Barnaby is the president of the IBIPSA. It's a very important association that promotes the use of building simulation. If you have a question, I think we have 3 minutes.
Well, thank you.
Good afternoon. Thank you to be here, and I will try to be as fast as clear as possible in a huge. Is it okay? It was here. On a huge item which is under the name of modeling tools and simulation, but I'm trying to touch the point of standardization versus open source building performance simulation tool. The main problem is that we are trying to have standardization in calculation to be comparable in the result. We have seen the problem just right now about the data, the information about performances for any kind of equipment we can use, starting from the chiller up to the heat pump and so on. But then I would try before to give a context where we are working with. We said we are in the field of building energy modeling. The building energy modeling is been taken from the IBIPSA United States side, in this case, just part of the definition is, you can see there, a wide building assessment of energy efficiency that use computer program for calculation, okay? Then usually we have two steps. We have to build up entire building model. This building model is introduced in the computer use a specific tool, and then the task of running the model is just the simulation. Then the result of the quality of our calculation depends on two main items. On one side, the quality of the model itself, what kind of physical-based model or statistical-based model, the detail we are going to put in this model, and so on. And this is inside the computer code that we don't see, or we can only understand reading sometimes the manual. Not even we have so-called engineering manual where we can have such kind of information. And on the other side, depends how much the building model is comparable to the reality. If I have a sphere and I'm going to model a cube, of course the result will be not consistent because I just use completely wrong description of my system. The second depends strongly on the user, the first depends strongly on the quality of the computer tool we are going to use. Now, what is a building performance simulation tool? A building performance simulation tool is just a computer software tool that, through simulation, allows to perform a building energy modeling, then to assess the performance of our building. We have some important keywords we have to remember, which is the computer model. The computer model, as I said before, is a collection of algorithms, equations, able to or used to capture the behavior of the system being modeled. It's our building model. Then we have the computer simulation, as I said before, is just a way to run the model, the computer model, on our specific computer using specific program. Then we have the building performance, which is the goal of our simulation. And we have to remember that it's not only energy, the goal, again. Then mainly we have to look for indoor environmental quality, then energy and other things, and so on. Then quantities we are looking for are time evolution, temperature, comfort indicators, low profile energy demand, and so on. Now, we can have a lot of building performance simulation tool, which can be classified in different ways. Then, for instance, we have simulation engines. That means mainly the program has been built to produce the calculation, not very simple user interface, and not interface at all, like Energy Plus, like it was trans at the beginning, like SPR for a certain way. IES is something in between. It's a mixture of what I said. There is its own engineering calculator, but also interface, etc. For instance, we can have libraries for general purpose tool, like the LBL building library to use inside Modelica, or we can have just software hosting simulation engine by direct call or via interoperation through files and so on. Now Revit is trying to do that somehow. Design Builder is doing that. It's just running on the behind Energy Plus, no, on the interface. Well, the point now is that there was a wrong engine inside. For that reason, I put the cross on. The point is that by law, why I mean by law? Because we have an energy building performance directive, which has been enforced in each state with local law, national law, and we have to use a common tool to assess the energy performance. Then the European Commission has paid for, we can say that, has paid for SEN to try to provide standards to have these common tools. And then we had the previous standard. Now we have a second set of standards. Up to 60 standards has been released last year for this energy performance calculation. And also ISO was involved for a part of this standard. And then we have, for instance, EN ISO standard 52016 part 1 and EN ISO 52017 part 1, which are expressly dealing with the performance, not only in terms of energy, but also in terms of cooling and heating load. And the first one is the calculation procedure we have to follow for the energy assessment according to the directive. And the second one is more general. It's called generic calculation procedure, which should be followed if you like to build from the scratch a computer simulation code, let me say that. The problem is that we can choose to use differently among Europe according to what we discussed also before, that we have national annex, and we can say that here in Turkey, for instance, you can use the hourly simulation, the hourly calculation. In Italy, you can use the monthly calculation with different algorithms, for instance. The problem is when, as we had in the past, that each region in Italy could choose its own. Then you can imagine what you have, not really a standardization. Then the point is that coming back to the hourly calculation, which is close to what we call simulation of detailed model for the performance assessment, the problem is that the standards are too simplified and not enough validated in the way that has been written, but I couldn't find any references, I couldn't find any paper, I couldn't find any report showing the quality of the proposed algorithms. And you can understand now why. Then there is an extent, just the only reference to validation is as user. When you are going to use the standard, when you build up your model, you have to check against the ASHRAE 140 standard, which is the so-called best test, which is a bit old test, I would say, very old test. On very old data, very old model, is comparison among different models and so on a very simple case. Then the main problem is, for instance, looking at these standards, that, for example, heat transfer through a wall has been chosen for the hourly simulation, a Lampert parameter explicit scheme. Well, where we have a fixed number of nodes, up to 5, fixed resistance, doesn't matter what kind of wall you have. You can understand better from this diagram. You see that the wall is modeled with 5 nodes, 2 on the surface, internal, external, and 3 internal nodes. The resistance, when you calculate the overall resistance, this has been split in a fixed way. Doesn't matter the real wall is made, how many layers, how the layers compound, and so on. Then you have a certain degree of freedom on the capacitance. Then you can have up to 5, but you have to choose in the way that you can have only internal capacity just on the surface. You put all the capacity of the whole wall there, or you can have an external capacity, or you can have 2 internal external capacity on the surface, or you can have distributed capacity or equal, regardless the real distribution of capacitance inside the wall, or you can have just only one in the middle. And then you have to choose this according to a national annex you have to prepare on national basis according to the weight of the wall. You have to use model 1, 2, 3, 4, 5. You can understand what kind of result you can get out of that. And if you look on to the detailed standard, which is the 52017, the only thing is just showing a nice heat transfer equation, differential Fourier conduction equation, and say that, okay, any kind of solution you can apply is good enough if you are able to show that it's complying with the best test, which is an integral test on the wall building, not specifically on the heat transfer through the wall. You can understand that it's really unuseful as a standard. Then, how we can overcome this problem? From one side, the directive is called to have a common method and SEN is delivered such kind of standards. On the other side, we need performance simulation to better understand the system performance. We have heard just this afternoon that people expect to have very fast response system, 5 minutes to adapt themselves, okay? And then means that probably if you like to be able to perform such kind of system is not enough 1 hour time step. We have to go down to 1 minute time step. That means we have to move to performance simulation through the tailored adaptable building simulation tool. That means we say, well, okay, we have enough, we have seen. We have Energy Plus, we have Transys, we have ESPR, and other tools. We can try to use one of those codes as a reference code, as a standard, I call de facto standard. Everyone is using, everyone is happy to do that, then it's a standard, because everyone is using that. But then it's very difficult to choose, to make a choose, because you can produce what we call a market distortion. There are software producer, commercial software producer, for instance, applying for the low necessity, no? Then you have specific software for the calculation for the BPD low, and so on. And then if you try to come into the market, you are going to have a lot of complaints from the technical software house. Then it's quite difficult to, but there is a possible route to solve this problem, and this can be to have an open source community with an open source code, which is just trying to build commonly in a very open way the tool. In fact, we can see that open source means that everything can have the source code, everything can work on the source code, everyone can give out the source modified code if it's recognized a certain number of rights and so on. But the main point is that normally open source means collaborative effort, means to build a community, open collaboration. And open collaboration is the only way to get a real standard in this field, because you cannot imagine to have, let's say, a pile of written paper you have to translate in code, in machine language, in programming code, and make validation. It's not the way. We cannot produce a tool, a simulation tool, just writing standards. We have to produce directly the code. And then we have to find a way how we can produce this code in completely agreed way to be de facto standard. Now, of course, the potential is very interesting, but also we have some pitfalls, because potential is the code is public available, that we can have a large user community and developer community to have feedback and to correct errors and so on. On the other side, of course, you cannot schedule in a tight way the work, because it's normally not paid work, and then it's a volunteer work. Only if you found a foundation which is founding, then you can schedule the work. But it's possible also to build up a foundation. Then to be able to work consistently, the major point is to build a community of developers, users, and to have the way to communicate efficiently to be able to build this code. Now I will show an example. This is more than an example. It's a project. The project is on the halfway, we can say, is an open source code that's being developed with this idea behind and with this object in mind. The first point, as I said before, is how we can share the code. And we can share the code using the so-called software forge. Software forge means we have a repository where we store the code. The code is accessible to everyone. And of course, as a user, as a developer, you must be registered, follow some rules, and then you can upload your suggestion, you can upload your modification. There is a way to keep note of everything and so on. And also, again, we are not going on the market. We are using open source tools. We have a nice source, open source tool, which is Software Forge, Allura, from Apache Foundation, which is freely available, which is doing perfectly such kind of work as a repository for the code. Then you can see here, we have tried to develop such source code, open BPApps, Open Building Performance Simulation. It's a performance simulation program designed as an open source code cross-platform. Cross-platform means that you don't need to recompile if you have the Exe code for any different platform, if running on Windows or on SX or on Linux. There's a simulation engine. We're not interested to work on interface. The problem is, again, we are not going on the market as an actor of the market. We are providing the engine, okay? A common engine anyhow can put inside its own code with its own interface, with its own language, its own database, etc., etc. Just the engine, the calculation engine. And it was coded from the scratch using object-oriented programming language. We'll discuss it briefly later on, C#, implementing naturally from the beginning parallel calculation. Because today, my phone here has 8 CPU. And normally when I'm using Energy Plus, I'm using only 1 CPU. That means if I can use my phone, it's faster with a CPU in parallel, it's faster than running on a PC Energy Plus, because it was coded when parallelism was not there. Okay, then this was the reason to use object-oriented modeling, because working with object, we can naturally go to parallel calculation. Naturally, we can go to easily add components in our system, because an equipment is a component. I can pick up from this is one solution, for instance, about the data and the data security, performance data of equipments, because I can download directly the object code embedding the data from the constructor, and then I plug in my code and run it. That means I'm not anymore involved in putting inside the data. Who's responsible for the data? The constructor, the firm, the factory, as they are responsible for the machine itself. Okay? Then there is no questioning about. Then what is behind? What normally we have, that means the building, naturally, if you are looking at the envelope, the wall are parallel system and not serial system. Then each wall can be simulated parallelly. In parallel, that means at the same time, how many CPUs you have, you can calculate a wall at the same time, and then you put the data together in the energy balance equation for the room, so-called air temperature node or whatever. Then the point is also that using object in this way, they can run with their own internal time, different from the simulation time. What I mean? I mean that, for instance, if I'm using 1 hour time step for simulation, if there is a subsystem which have an internal time, which is some minutes, it will work probably with some minutes time step internally. But from the outside, it will exchange information hour by hour, and so on, all differently. Can be 2 hours, the internal time step. For instance, if I'm going to look for heat transfer into the ground, no, it's unuseful that I'm solving the problem at 1 second time step. Doesn't make sense. I can work with maybe 5 hours, 6 hour time step in that case, and just exchanging the information outside. And then I can optimize the performance. About the language, I said we choose C# because it's an open source language, because we can have cross-platform optimization, because it's not really compiled. When you compile and have an Exe code, in reality it's a pseudocode. Then it would be really compiled when you run the first time on your own machine. The net framework is so-called JIT compiler, just-in-time compiler, which is really compiling, optimizing for your CPU, for your operating system, the code. That means you can have the best optimized solution for any kind of computer you're just using. And also C# is an open source language, and also you can have a free developing interface or environment like Visual Studio now from Microsoft is free to use at a certain level, and also you have similar Mono, which is similar environment on Linux machine. That means you can develop on both, or you can use on both anyhow. Then the structure, I will give faster on this part because it's not so important in my opinion. Of course, we have a project. When we have a sub-project, we have different libraries. You can say numerical library, manager library, component library, utilities library, and then 2 sub-projects related to developing, testing, and so on. The simulation manager is the kernel, the core of the simulation system, because it's handling all the information between each component and the well-building description. And of course, it's controlling the workflow, it's controlling the parallelization, the calculation, etc., etc., etc. This is just to show how you can manage the simulation in parallel at different levels, at the zoom levels, at the well levels inside each room, depends how many CPUs you can use. Of course, it's based on a classical solution of energy and mass balance equation, but the main point is that when you are dealing with the wall being object, you can choose the method you wish. That means you can use finite difference, you can use theta method, you can use explicit, you can use implicit, you can use transfer function. Okay, that's it's up to you, depends on what you are doing, what's your preference, and what is faster for your condition. Of course, internal gains are taken into consideration and so on. The system side is serial calculated, because the system, it's if you have 2 parallel systems, you can go really in parallel. Another way around, it's a serial connection. That doesn't make sense to try to parallelize the part looking regarding the system. The other point is optimize the way that the so-called information chain is respected. This was what I was experiencing when I was a transit engineer, that if you put in the wrong interconnection, the serial connection between components, then you get a strong instability. The main point is that we are still developing the part regarding the system simulation, because we are trying to work really on dynamical, what we call through dynamical models for system components. Because up to now, we have to remember that the only system components which are truly dynamics are the storage, the water storage, the rock storage, and in some cases, the pipe distribution with water. No other component, we discussed before, performance map. Up to now, performance map doesn't consider any characteristic time of the system. This is the important point, because sometimes we say, well, we have to go down with the simulation, I said before, at 1 minute time step to be able to catch some performance of the system. But if we do that, we are going against the physics of the problem itself, because the so-called steady state approximation is not anymore valid for the system. If I have a system integrated with on 1 hour time step up just at the limit, no, depends on what system I'm talking about, to be able to use steady state description to have a right dynamic answer. On the other way around, I have to consider capacitance, I have to consider characteristic time. Then this is an open question, because we have already an experience on this. This is a standard on solar collectors, that we can have a performance curve with a capacitance term. And then if we move in that direction, performance curve with capacitance term, we can have better model. Till we have that, we have to try to model the characteristic time effect. Now, contributing to new development, I said it's very important to grow up a community to be able to cooperate using the open source approach and to recognize that this is the only way in which we can share really a unique way to perform calculation completely agreed by everyone, and this can be then a de facto standard. The process of developing is, of course, under control. That means there are some rules to follow. We can upload this new part of the code. This will be checked and tested by other actors to qualify the result, in the way that only after this procedure, we will be part of the official repository. Then, just to give an idea, we have built this code. We made the so-called verification through the ASHRAE 140 standard, as required by the European standard now, and you can see that we have a good agreement. Different cases. But the main point is that, in my opinion, and in our opinion, is not enough this to qualify the code. For that reason, we're using another very interesting tool, is a report still from ASHRAE. We also applied and improved, where you have example how to compare performance result against analytical calculation and so on, for each bricks of the fabric at least, not up to now for the system. Then, conclusion and perspective, an object-oriented building performance simulation tool has been shown as a possible solution to have a common standardized tool to satisfy the PBD requirement first and to be a generic tool later. And a joint venture between the community of this tool and the technical software house, just providing this as an engine they can include in their own product, can be a solution to have a unique tool without having marketing distortion and questioning with the technical software house. Thank you for your attention.
Thank you, Livio. I think we have the time for one question. Hi, you are a member of the board of IBIPSA.
Yeah.
Your proposal about the open source are already discussed in the board?
Well, the project we discussed, but we had to wait because the project was partially funded by Region Lombardia, and I got the permission to open to the world just 3 months ago. And then a round of, let's say, interview with, for instance, the National Energy Agency, ENEA, to come together, for instance, to continue the developing of the code. Then there is this round of discussion how to try to give more, let's say, evidence and utilization. Then, of course, we already discussed, but we are waiting to see if we can add other, let's say, formal recognition from the National Energy Agency and support.
Okay, thank you, Ray.
Thank you.
From the University of La Rochelle in France.
Thank you.
The evolution of modeling and simulation tools.
Thank you, Mr. Chairman. First of all, I want to thank our TTMD friends for the invitation. It's always a pleasure to share the warm TTMD hospitality. Thank you. So, what I'm planning to do is just to try to discuss 3 points, in fact. So what are the primary drivers for modeling in our domain? What are the nature of building energy and environmental systems and the evolution in simulation, and what should be highlighted for future developments? Of course, it's just a point of view. So
I took the French regulation because, of course, it's the one I know better. If you look at the evolution, for instance, after the oil crisis, we have seen the creation of building regulation in different countries. And the first regulation was just prescriptive. It was a minimum insulation. So very simple tools was necessary. But very quickly, we have been dealing with heat losses, including ventilation and filtration. And very quickly, heating needs. So heating needs is how you recover the free gains, how you play with the inertia. So we have been developing very quickly tools in this domain. And very quickly then, global performance. So energy used. So the coupling with the system start to be a problem, and so we had to focus on that. And then we integrated the European methodology, so we changed our mind from cubic meter to square meters and so on. And now, in the new regulation, we're focusing on low energy buildings, and even in the last one, on we call E plus C minus, on low carbon print. So you see, European level, it was late. It was only in 2002 that Europe focused on our problem. And I remember we made a study at the time in 2001 with Claude Allard from Switzerland, and there was a huge dispersion of methodology in Europe. But you can see the evolution, and now we can see that in all EU initiatives are strengthening the role of building sector right now. Until the last new EPPD we are looking for, now we are waiting for, towards the smart buildings or smart readiness indicators or things like that. So we have work to perform. So it's for sure that the energy policy have been the main drivers of the evolution in building simulation. In our case, the industry has been using the building simulation, but it was not the driver. However, the energy is not the only driver. More and more, we are focusing on health, comfort, quality of use of the buildings. So we need new developments. At the same time, I show this curve, it has been presented already. Here, the evolution of the computer efficiency. Since I started my PhD in 75, the increase is about 1 million times. So of course, it has been also a strong evolution of tools we have been able to use. Very briefly, the evolution of the building energy models since the pioneer works of Stephenson and Mitalas, for instance, in the 60s for developing the response factor through the energy demand. So I follow the same tracks during the 70s. Energy supplies in the 80s, so development of the code we know, BLAST, DO, E2, ESPR, and so on, at the same time. And then we have been focusing on integrated new energy sources, for instance, and at the mean between the two, also we have been tackling the multi-zone transfer inside the building. So we merged from monozone codes to multi-zone codes. Most of them were not taking into account, for instance, the airflow through the different zones of the building until very recently. And then in 2000, the main idea is to couple these models with another community which was developing at the same time, which is the IEQ community. And I put it here also. So you can see that there is the same evolution. So in the 70s, we were working on bioeffluence control. Then we have been working on particle deposition, VOCs emission, and then the exposure. And then we needed the multi-zone codes like COMIS or CONTAM, for instance. They were developed at the end of the 80s. And now we are coupling this to more general codes, for instance, for the local climate and so on. And in fact, these two communities, they merged very recently, in fact, to tackle the indoor environment quality, long-term performance prediction with intelligent control, for instance, friendly interface for designers, virtual design studio you were talking about, integrating other platforms like Modelica for the system and so on. But I wanted to say these two communities, they have been merging very, very recently, in fact. So what are we dealing with? Building energy and environmental systems, so it's multi-scale in space and time, multi-factor, multi-performance objective. It depends on your objective, of course. Multidisciplinary, multi-purpose application from an application point of view. So if you like at the scales we are facing, we start with the climate, in fact. And the boundary is the local microclimate, the neighborhood, let's say. So the scales are days, and the dimension are thousands of meters. And then you are approaching the boundary of your building. And so the scales for the building will be hours for time and few meters for the dimension. And we are trying to solve the interface between the microclimate and the building. And then you enter the building and you have the same thing. So you are looking at zones. So the time constants are minutes, let's say, and the dimension are meters. And then you look at indoor material selection, room conditioning, for instance, ventilation. And then we are close to the subject. And then the scales are very small. If you are looking at turbulence, for instance, and the scales will be millimeters and less than 1 second. So we are facing this complex domain. And of course, what we are looking for is the occupant satisfaction. So the goals are indoor environmental quality, energy, less and less, I will say, energy, and safety and security. So multi-factors means we have to take into account these different factors, but how do they interact and impact the performance? So we have to be able to build the links between these different factors. Multi-performance. If you want to evaluate a performance, you need a matrix, you need indicators, and you have to refer to some matrix. So it could be the standard, it could be a label, it could be something much precise. But you have to define the indicators and the matrix. Multidisciplinary, of course, if you are building a new building, so you will have the architecture and design team, you have the engineering, the system design, you have the project management team, and your tools should link these different teams with a transfer of knowledge, with a human interaction, and a transfer of data. Of course, a building is also multi-stage of purpose during its life. So we have the systems, we have the actors, and we have the actions. And you have to, so the modeling, the simulation is not focusing on the design for me. You have to follow the building. We were talking about monitoring, for instance, how you follow the evolution of the building all along its life. So that is a problem. So what should be emphasized in the future developments? So I put just point of reflection. It's not just ideas. The first challenge is the evolution of models towards an integrated real building performance evaluation. We have been talking during the World Conference of integrated design and so on. So how do we manage this? The second challenge is we have two problems. Long-term prediction of very small-scale phenomena and the prediction of the control of these phenomena. And the challenge 3 is coupling with environmental models. We have seen that we are within boundaries. We are solving the boundary between the climate and the microclimate and the building, the whole building and the zone to the occupants. And challenge 4 is improve the confidence in prediction. We have a real problem in our community in this domain. And finally, I will discuss something with you with what I think we should focus on is the occupant-based modeling. So changing from Eulerian to Lagrangian approach. So only a few ideas. Evolution of models towards an integrated whole building performance, which I call the whole BIP. When you are looking at modeling and simulation, the objective is to improve, in fact, the design and the management of the building. But at each step, you don't need the same information. So we have to adapt our models to the need of information at the very, very early stage of the design. You need information about orientation, influence of the shading, and so on. And then more and more data is involved in your model, and you will have to answer to different questions. So it's something very often we are missing, but we need, in an integrated approach, we really need this. And then we developed with some colleagues the CHAMPS initiative a few years ago. It's combined heat, air, mass pollutant simulation. And we developed with the colleagues from Syracuse what we call the virtual design studio. So the idea was to put inside different models and to couple these models with different kind of database in order at each step, in fact, the answer we were looking for. And it was applied on the building built in the Syracuse University. And the idea was to have, at the same time, different answers to qualify, in fact, the evolution of your project. Of course, much more work is needed in this domain, but I think we are very close to this kind of multi-criteria approach. Long-term prediction and control of very small-scale phenomena. We all know the limits of CFD. I have been developing CFD codes for 25 years. If you want to model this room, for instance, and to respect the physics, it's quite impossible today. We have to use turbulence model, we have to use, and so on. And these models, usually, they are not well adapted to our problem, which is a mixed convection problem. So we have to be careful. CFD is very useful to get an image, let's say, but for instance, you cannot follow a phenomena with CFD. So the evolution in the last year, so many tries in the domain decomposition, the fast Fourier of Chen also, and reduced order modeling. So I will focus on the last one. The reduced order modeling it's quite simple in the concept. So you project, you make a simulation, so you have your instantaneous field of velocities, for instance, and you project on a smart basis of orthogonal vectors, and then you get all the decomposition of your vectors on this base. If the model is consistent, then you can use this model to reproduce very quickly the evolution of the field. So it's what has been done in our domain for years now. Here is a result from a colleague, I cannot remember the name. It's a colleague from Syracuse, Candy. Right. And so you can see that it's quite consistent. And what we did, we used it for control. So when you are controlling, for instance, the temperature of this room, you put a sensor on the wall, but you are looking for the comfort where you are. So how can we play with this kind of tool in order to check the quality, of course, of the temperature field in the occupation zone? So we did that a few years ago. So the idea is, of course, there is offline work which is quite heavy. We are using large AD simulation in our case, for instance. So it's sometimes I put 90 hours in this case, but it could be hundreds of hours. But then, once you get your model, your reduced order model, to run it, it's very quickly. It's very quick. And so we used it in a control loop for the first time, I guess. And you can see the results here between the direct LES simulation and using this controller with the reduced order modeling, and we have quite the same results. You can apply also this same kind of idea for our domain. If you want to optimize, for instance, a building with environmental criteria, energy, comfort, etc., you need thousands of simulations. So the idea is the same. I built what I call a meta model. So in this case, for instance, I use the experience planning design. You know the number of parameters, you know the limits of your parameters, so you can plan the number of experience, numerical in this case, experience, necessary to reproduce correctly the phenomena. It means that you are able then, when you have this basis, to develop a simplified model, so it could be linear, it could be any kind of model, optimized in this sense. And then you can use it directly for multi-criteria optimization. Because even if you need hundreds of simulation with transits, for instance, it's not so complicated today. You can couple with Python or other code. You get your basis. You have, of course, to check your meta model, but then it's very easy to make optimization. So if you couple with environmental database or cost database, you can look for the best solution with different kind of criteria. We applied it for new building, for retrofitting, and we are working on it for assessment of building performance now, introducing occupants' behavior and so on. The third challenge is the coupling with environmental models. Most of the simulations today are made as all the buildings were built on airports, because you are using climatic data, which are not the real data of your building. So we are facing this problem, and we propose some solution. So there was a pioneer work a few years ago, one of my PhD, in a European project. We were looking at the microclimate in Athens. So we developed zonal models for the canyon, the street canyon. And I present here the results between the measurements and the code, and it was quite good. So then we went further, and we have been tackling the whole design of urban district, looking at, in fact, the bijective influence of the microclimate and the building. And so we have been working on Lyon performance, for instance, for a while, and in Nantes also. This example is in Nantes. And then we are looking at microclimate analysis, and we look at, so here you have the cooling needs, for instance, for the buildings due to the microclimate, and you can see that it can differ from one building to another. And also, we evaluate different kind of strategies. For instance, if you are using green roof, what will be the impact on the building on the microclimate? And you can see here some results. The fourth challenge I mentioned here is the the necessity to improve the confidence in prediction. We have many sources of error. The model itself, how you reproduce by a model the reality. The quantity we are using, the quality of the data, of materials, of material, and so on. And also we are impacted by non-deterministic features, like human occupants, for instance. And there is a very huge question about the quality of the prediction of our models. It's not recent, but it's not really solved because there is no tradition in our domain. There is a very strong community at international level in this aspect, a general aspect of accuracy of the models, but not in our domain. So we had a few pioneer works, but we need really methods to quantify reduced uncertainties in model predictions, and we need methods to calibrate models with minimal measurements in near real time in this case. And the fifth challenge is just a thought, maybe a dream. We are all, during this conference, everybody was saying we have to focus on the occupant. We have to focus on what we need really in the building. But in this case, why do we not change our approach, the Eulerian approach, so we are looking at the building like that, but we are not looking at the occupant, and focusing on the occupant, and following, in fact, the occupant. And for instance, it's exactly what we need for IAQ. IAQ is not a problem of building, it's a problem of exposure. So I think we have to think about it. I tried already some pioneer work, but I think we should focus on this idea and see how we can evaluate. So in order to conclude this, I put that for many years, building energy and environmental modeling and simulation have been driven by the evolution of building energy policies and demand of the industry, but less in our case. In our case, it has been driven by and there is a confusion with most of our colleagues because they are confusing the, let's say, regulation models. You have to qualify a certain performance of the building with a set of hypotheses, and the real simulation of the behavior of the building. So we have to think about it. And today, this policy are focusing more and more on performance, so energy, global performance, and we were discussing. But there is a social demand of healthy, comfortable, and easy to use building, for the quality of use. So we have, this is, in my opinion, the energy is not the main topic today. We know how to build efficient building, but the quality of the indoor environment, the quality of use, sometimes is questionable. So it's a different kind of approach. So we need to answer. This is our job as a scientist. But performance means metrics, definition in many aspects, confidence in our prediction, multi-scale from micro to macro scales, and multidisciplinary. And developments in the internet and mobile technology, we have seen few presentations on that. I think they can offer some interesting issues with the mobile approach to focus on the occupant. Thank you for your attention.
Thank you, Francis, for your very interesting contribution. I think we have a lot of questions now. No question?
No.
Manuel, perhaps?
No. sure.
Really, we had okay, some time ago I worked in the revision of the Portuguese regulation regarding indoor air quality. And this was like a discussion we were having because we were, for instance, if we use the analytical method for the calculation of the ventilation requirements, really we are making something based on the average concentration of the pollutant in the room. And for instance, if it is a school, we are considering intervals. But during intervals, students are not there. And so we are using in our calculation some data that makes no sense. So it's really, okay, I fully agree with you. And really, tomorrow I will present something that is in line, because we have a system, but we have a kind of measuring station that we can move from place to place inside the building. So the data about outdoor, it's a fixed station, but the data inside the building, it's the place we want to analyze in each moment. So it's, I fully agree with your trend line.
Thank you. Marco? Yeah.
Please, Marco.
Very short.
Very short.
Marco Perino from Polytechnic Torino. Thank you, Francis, for your very interesting and stimulating presentation. I have a question about meta models and model reduction. I've had the opportunity to follow ISVC conference in Melbourne. There was Cheng, and I saw a lot of presentation about this method. So it's becoming very popular, but it's very interesting. As you saw, it's very reliable. My only thought is that how much you can generalize it, because you built on a specific project and on a specific building.
No, not completely. Yes, at the beginning it's exactly what we did, but it depends what kind of parameters you introduce, because I prefer, because there is different kind of approach, neuronal approach, by apprentissage, we say in French, I don't know the name in English, but I prefer the kind of system I presented, because you built your design, you design your experiment, in fact, you define all the parameters, and in the parameters you may include geometrical parameters, for instance, because you have to put the limits, and then you design your experience, so you know how many simulations you need to get a good mapping of your domain, and then you use a meta model, so you select a meta model to reproduce it. So you keep the information, because then you have the influence of every parameters is there. So it's not only, it's more flexible than I thought when we started, let's say.
I think we have just a comment from Livio now.
I should use this for it works.
Yeah, it works. What was partially my question. The point is that it was in 1984 up to 1988 that we had in ISPRA 3 workshop about parametric identification, okay, and parametric model and parametric regression, regressive model, and also neural network. Creator was very interesting on that, was doing such a lot of work, and nothing we have today. Why? Because when you use reduced order model, what you're doing, you are fixing some feature of the system and leaving, as you said, only some feature free, as a free variable. But if you don't know from the scratch, from the beginning, what could be really the important parameter, then you cannot have correct result when you move it, first of all. Second, if you cannot use this request order model, you train it on a certain kind of building, on a completely different kind of building.
No,
you restart the training from the scratch again. Then I fully agree that's the only solution for online control. I fully agree with that. You need a very fast model, but it's not for the design purposes, in my opinion. Because it's something which is a lot of the training, how we are going to select the parameters, to give freedom or not, etc. Then you cannot really optimize. Because if you like to optimize, I'm finished. If you like to optimize, you have to give freedom to so much variables that you're back to the physical model again.
Yes, but well, the experience I have for a few years now is that at the beginning I completely agreed with you. But now what we can do is you can do at various levels. So you may put a lot of parameters at the beginning, then you have a first meta model, and you can see the real influence of every of your parameters you selected with their boundary, because you have to put the boundaries. And then you can build a more reduced system. It could be with 100 parameters, or 50, or it depends. But of course, you will never pass from a single house to a tall building. That's for sure. But with a certain, for instance, we have been working with social housing. Social housing, the sketch are not so different because with the year of construction, you have roughly the same kind of characteristics. So you can already work on a large basis of buildings. But we can discuss later.
Okay. Thank you again.
Thank you.
No? Harputlugil from the University of Ankara.
Thank you so much. Good afternoon, ladies and gentlemen. I would like to thank to you. Till that time, you are now here to listen to me. And my name is Gülsu Ulukavak Harputlugil. I am from Çankaya University in Ankara. My presentation title is A Critical Analysis of Turkish National Calculation Methodology Software, BEPTR2, from an architectural perspective, actually. But I just want to be a bit shift my focus to the energy calculation, performance evaluation, and why we need it. And actually, I'm really lucky that most of the things that I would like to just only touch here were already explained in detail with these professors. Thank you so much. And also, in order to be, I have a very limited time, so I just want to be serious, so I'm going to go through on my text. I'm sorry. Okay, as all you know that currently a climate change issue is a reality for our world, and individual attempts have not been enough for us already. So international agreements on the solution ways of reducing carbon emission and increasing renewable energy technologies are done at the moment. So the recent agreements during Paris Climate Summit guaranteed that the European Union will cut its emissions by 40% compared with 1990 levels by 2030. And when we look at the United States, they will guarantee that they will cut its emissions by 26% to 28% compared with the 2005 levels by 2025. So actually, what we would like to talk about, sustainability, this is important that what Edward Mazzarella said, that it is still necessary to convince the designers that getting sustainable buildings is a design-based approach rather than emphasizing technological solutions or prescriptive requirements. So we need to, as an architect at least, we need to look from that perspective. So if design-based approach is important and design is a key issue for us, we need to consider interdisciplinary team. which works together from very beginning of the design process. In a traditional way, after almost all decisions are taken by the architects, the project is sent to engineers for necessary calculations and system design. However, a new way of thinking must be adapted in order to meet the goal of reducing carbon emissions and enhancing the energy efficiency associated with buildings. The solutions can begin with integrating four possible methods. None of them work alone, and they are not all relevant in considered every strategy. However, considering the following tactics may be necessary: reduce the overall energy use in buildings, specify energy efficient equipments and technologies, use renewable strategies and purchase green power, educate building owners, operators and occupants, which is very important, that education. And if it's possible to integrate those methods, it's a big step. If it's possible to integrate those methods, it's a big step taken for gathering performance-based buildings. The key to a high-performance building is optimization and integration of all things, whether fan speed or fire safety, whether landscaping or lighting efficiency. It means things on both a micro and macro level about how building systems interact and how building occupants interact with those systems. If we talk about performance, we need to take a quantitative-based evaluation, which needs numerical comparisons and calculations for sure. Considering performance evaluations, there are several levels that need to be aware of. This is a pyramid of this detail level, actually. At the bottom of that pyramid, simple calculation tools, which are helped us to define basic and mandatory energy demand for buildings. If you need more detail, multifunctional analysis for evaluating buildings, for instance, regarding energy building certificates, you need to use simulation tools that have capacity to analyze in detail and mostly in hourly basis. If you turn back to the performance-based design, at the bottom level of mandatory performance evaluation is energy efficiency and energy performance of buildings. From that point of view, today many design-related tools can be analyzed through the use of design tools. There are several basic issues addressed by that tools. Some of them consider only one of those items, which are listed here, actually. Some other very detailed analysis tools consider interrelation of these items. And they directly or indirectly affect one another and overall energy performance of a building or service systems. If we come to the specific case that I would like to talk about related with Turkish regulations, regarding all those information about performances, analysis tools, in the light of introduction of Energy Performance of Building Directive of European Union, Turkey has released Building Energy Performance Regulation in 2009. Moreover, the related national calculation methodology and its tool called BEPTR became mandatory in 2010. Early researchers executed with BEPTR stated that the software needed to validate and should be tested. Regarding those analysis studies and considering several issues occurred during practice, national calculation methodology was renewed in 2014. And related software has been updated, actually. The second generation national calculation method, called BEPTR2, the second version of it, was now open to use, authorized users for energy certification. And the methodology of that covers for sure that the loads of the buildings, systems analysis of the buildings, the energy consumption caused by ventilation, daylighting effects, and also calculation of the lighting energy, and also energy related with sanitary hot water. Based on those relationships of the issues, general principle of BEPTR2 is here, actually. There are mainly two parts were interconnectedly to each other. The calculation process, authorization and certification happens at that part. At the desktop part, it's possible to model and evaluate the building before sending for approval. If you think that just after you modeled your building, if you think that it's okay, then you send it to online module to make ready for certification. The desktop part where the modeling is occurred is more critical from architectural points of view, actually. So as a user-based approach, I just want to give information about from that part. The building definition process includes several sub-modules as definition of the geometry, which can transfer CAD drawings as well here, but only in a plane part, and solar gain modules, ventilation, internal gains module, heat transfer modules are the other sub-modules of it. All of those modules, interaction is here showed. I'm not sure that you can able to read it, but all information is used to define loads of buildings in order to for calculation for the net energy just after. As a load, these all modules are calculated. And actually, here are the building energy performance regulations objective and BEPTR2's capacity to overcome with those requirements. Here you see, for instance, as an objective, it's good to evaluate or consider the climatic conditions, meteorological data, especially related with solar control or solar gains. But unfortunately, evaluating climate conditions are not possible with BEPTR. Okay, we have climate data there, but solar shading elements can be defined, but it only have to consider solar control, that's all. Related with ventilation and natural ventilation, solar heat and light at optimum level, the objective. Actually, daylighting capacity and natural ventilation opportunities are not evaluated again in BEPTR. So think about that. What are the objectives and what the still the capacity limited of the BEPTR2? What else? For sure that, of course, building envelope calculations are possible with it, but only the means of U-value calculations in steady-state conditions. So it's not possible to evaluate thermal capacity, which needs dynamic state calculations. What else? One is also related with the evaluation of the renewable energy systems, sources where building will be constructed. So, and of course, it should be also evaluated from the innovative perspective. So it's not possible to make any innovative design of the systems by BEPTR. Actually, as a summary, as an architecture point of view, there are two angles. One is local issues. There are three main issues that point that needed to be considered. One is modeling. Models should be simple enough, but should not be simplified. 3D modeling is important, and BEPTR2 allows designers to draw each levels of the building in its environment. However, 3D expressions are quite weak. The second one is calculation process. This is also related with the input parameters and how detailed defined those. If you're considering architects to use this kind of tools, at the early stage of design, it's almost impossible to define HVAC systems, for instance, in detail. So there needs to be a defaulting process. However, tools should be reliable enough at that point. Analysis of results is a critical part of evaluation. It's necessary to understand what we give as an input and what we get as an output. The results should have an ability to give advice for the further stage of design. It should be noted that here it's important. BEPTR2 is located at the bottom of the pyramid, so it's obvious that it has a very limited capacity to overcome with those expectations. At that point, we need to consider several other design-based tools which have opportunities to support architectural expectations and integrated into early design stages. This is really important. However, the other angle, which is global issues, need to be considered here. Nearly zero energy buildings, for instance, one of them. This was already defined in 2010 EU directive recast, but at the local regulations base, we are still not discussing anything about it. The other one is occupant behavior. There are many researchers executing about how integrated occupant behavior. However, we need to consider dynamic occupant behavior. And the third one is data gathering. Actually, today we discussed about here in the previous sessions about it. So I don't want to go that deep, but thank you for all of you listening. And I want you to think about a motto called form follows performance. This should be our, especially from the designer's perspective, should be our motto from now on if you want to design sustainable buildings. And the last but not the least thing that I want to inform you that if you're interested in building modeling and simulations, please feel free to contact with us. We are a new established Yapıda Turkey here under the TTMD umbrella. So we have a desk just at the other side of the door. Please feel free to contact with us for further details of it. And detailed information about Yapıda and Yapıda Turkey will be very soon in the social media and that links. Thank you so much.
Thank you. I ask for a question if they are, but it seems not. Sustainable design platform. Contribution is impulse ventilation system CFD analysis verification procedure for non-expert. Please, Ibrahim.
Thank you for coming. I will talk about a specific topic, actually. You know, CFD is one of the fundamental design tools in the industry, especially in the impulse or jet fan ventilation system design. But it's obvious that general HVAC designers have lack of expertise on CFD fields, and it creates some problems in terms of applications and in terms of reviewing these kind of analysis results. So I will try to give some insight about CFD analysis procedure, and I will try to give some tips and tricks about car park ventilation system CFD analysis reports. When we come across this kind of reports, how we're gonna review reports and how we're gonna get proper answers from the expert, actually. Main purpose of CFD and CFD analysis for car park ventilation system. Basically, I will be focused on fire modeling rather than the normal ventilation. So our primary purpose is to provide a clear approach route for the firefighters. So first thing first, we need to have a 3D model, then we need to create a computational domain, then CFD solver solve the Navier-Stokes equations, then we will get the results. Then when we start this process, we need to understand CFD experts' simplifications. First thing, you need to see some fundamentals elements of computational domain, like we have to simplify the geometry for the purpose of CFD modeling, but oversimplification creates some problems, like you need to see the downstanding beams or large HVAC ducts or maybe stationary vehicles. This is actually kind of discussion point. Some may say without vehicles, analysis may be more reliable because smoke will spread easily and you will be seeing the worst case. But at the same time, jet fan flow will be affected with the presence of the cars. So it may depend, depending on the CFD experts' understanding, but my preference is to model a car park with the cars. And other large obstruction must be included in the model. If you get such a report, you need to see these details in the reports, and if you are not seeing this kind of details, you need to ask, and CFT expert must validate his assumptions. Second thing, mesh generation. Mesh generation is a interesting topic, and there are many details inside it, but just I would like to give some insight. There are simulation there with same fire input, but we get different results. CFT experts must validate its analysis mesh size by giving you a different CFT analysis results. I mean, he or she need to make a mesh independent study. What I mean, you need to see different CFT analysis results with different mesh sizes, and CFT experts confirm which mesh size is optimum to answer this question. And physical submodel, it's a very complicated one. Most of the ordinary HVAC designers have no basic understanding about these details because it's complicated basically. But you need to ask assumptions, how you are modeling the fire. Are you using the chemical combustion model or a volumetric heat source model? Again, general consensus is to use volumetric heat source model for the car park fire modeling, but there is also some powerful tool. You may model the direct combustions. It's no worries. Both option is applicable. Just you need to ask CFT experts assumptions in order to be sure what he is really doing. And buoyancy model, since Bosinescu approach is constrained with the large thermal gradient, it is more appropriate to use equation of state model if you are modeling the fire. Turbulence, it's quite detailed topic, and all I can say, you need to see Reynolds average Nevers methods or large eddy simulation, because first order models probably get wrong results. But I believe no CXP expert on fire modeling field probably will not be using any first order model. And radiation model, CFT expert may use radiation model or may simplify radiation heat transfer by putting just a fixed fraction of total heat output. This fraction generally 0.2 or 0.3. It's 0.2 probably is more valid for general car park fire modeling. And design fire, there are many design fires assumptions in the literature, but these numbers on this table is generally reflects the consensus of the industry. It's 8 megawatts and the 4 megawatts, depending on whether you have a sprinkler or not in the car park. For time-dependent fire, there are some tests from European test authorities like British Research Establishments and TNO from Netherlands. You need to ask source of the fire curve from the fire expert in order to be sure whether he or she is using proper fire curve. You need to see one of these fire curves in his reports. And combustion products. If you are not modeling chemical combustion model, you need to represent fire products somehow in your volumetric heat source report, model. So one of the basic assumptions is the soot rate. It represents basically smoke. And this soot rate must be around 10–11%. It's a good representation of general composition of today's modern cars. And another thing, what must be the specific heat of combustion value? It must be around these below value, 24 megajoule per kilogram is based on these tests actually. If you review these test results, you may see many different numbers, but this is kind of average. Depending on your application, you may see higher or lower values, but CFD expert must validate his assumptions depending on these general consensus values. And initial or boundary condition. Initial flow condition must be evaluated. If you have any wind effect, it must be included analysis, and CFD expert must validate his assumption on this matter. Initial condition is important if your smoke flow affected by buoyancy somehow, you need to consider this or other way around. You need to see worst initial temperature and flow device. You need to validate your jet fan modeling assumptions. You need to see these details in the reports. And wall boundaries, as a general approach, most CFD experts use adiabatic wall condition as a worst case, but this sometimes leads problems because at the low level, it may predict different smoke layer depth. So other than adiabatic approach, you may use the constant heat flux with a constant temperature. And acceptance criteria. When you get the result, you need to accept these results depending on that specific performance criteria. I think one of the most detailed acceptance criteria described in the Singapore codes. These are more or less kind of collected from these codes actually, and you need to have a 10-meter visibility at 1.7 meter height, and to the center of the fire, you need to have a clear visible approach route. This is a kind of general consensus for fire analysis if you are designing based for the firefighting activities. And you need to see the details of the visibility calculation, whether you are calculating visibility based on the light reflecting object or light emitting object. And also there's a detailed and you need to see that you can see, or there is a number, just a number, but you need to see this number in the visibility calculation details, 8,700. You need to see this number. If you don't have any idea, just ask what's the source of this number and try to see this kind of report in CFD expertise. And jet fan velocity profile. This is important because the main thing is to simulate the jet fan behavior, and you need to see whether your jet fan velocity profile or jet fan velocity behavior is appropriate with the exact performance details. You need to ask these details to the CFD expert, and they need to include these validation studies to their analysis reports. And last thing, finally, you will see a post-process documentation, a final report, and this report must include temperature contour, visibility contour, velocity vectors, etc. Depending on what you are looking to achieve, you need to see all these details in your report, especially visibility and temperature details important if you are modeling fire. And jet fan velocity profile verification and description of model, etc. And also the result of the mesh sensitivity study. That's all. Thank you very much.
Thank you, Ibrahim. I think we must to close the session because the bus is starting for the gala dinner. I really appreciate more or less. I really appreciate all the contributions, so thank a lot for the speaker.
Yeah.